One commonly used data mining tool based on statistic is Benford Analysis. Today we have Benford expert, WVU Professor Mark Negrini with us. Professor Negrini, will you tell us about Benford Analysis?
Sure. Frank Benford was a physicist in the 1920s. He noticed that the first few pages of his log table books were more worn than the last few pages. He concluded that he was looking up the logs of numbers with low first digits more often than he was looking up the logs of numbers with high first digits. The first digit of a number is the leftmost digit. We have 32,340 students at WVU, and the first digit of that number is a 3. There are 9 possible first digits. 0 can never be a first digit, and minus signs are ignored when we calculate the first digit of a number. Benford examined 20 lists of numbers with 20,000 records in total, and these results showed that 30.6% of the numbers started with a 1, 18.5% of the numbers started with a 2, and this means that 49% of the numbers started with a 1 or a 2, while the other 51% started with 3, 4, 5, 6, 7, 8, or 9. He made some assumptions about the properties of numbers, and using some calculus, he calculated the expected frequencies of the digits in natural numbers. In the first position, there is a large bias towards the low digits. 0 can be a second digit, and so if we look in the second position, from the second position onwards, there are 10 possible digits. The bias gets less as we move on to the second and the third digits, and from the fourth digit onwards, the digits are equally likely for all practical purposes. Well, why is this so? If we take the Dow Jones Index at 1,000, where it has a first digit 1, we need a 100% increase before the 1 becomes a first digit 2. At 5,000, the Dow only needs a 20% increase to change the first digit 5 to a first digit 6. At 9,000, the Dow only needs an 11% increase before we get a new first digit 1 at 10,000. And now again, we need this 100% increase before the first digit changes to a 2. The Dow will therefore have a first digit 1 for far longer than any other first digit. Benford's law does not apply to all sets of numbers. For it to apply, the numbers must reflect the size of some phenomenon. Big numbers must refer to big things. There must also be no built-in maximum or minimum values, although 0 can be a minimum number. Tax returns, for example, have minimum and maximum values in various places. The numbers must also not be labels, such as highway numbers, social security numbers, or flight numbers. A data set that conforms very nicely to Benford's law is the populations of the 19,000 towns and cities in the United States. Every population count has got a first digit, and the graph shows the expected Benford proportions as the line, and the actual proportions as the 9 bars. Each possible first digit is shown as a bar, and the proportions are shown on the y-axis. The top of the bar is pretty close to the line in all cases, meaning that we have a very nice fit to Benford's law. Every number also has first 2 digits. The first 2 digits range from 10 to 99, and once again we use a line to represent the expected proportions, and the first 2 digits also conform closely to Benford's law. This graph shows streamflow statistics for 140 years that conform almost perfectly to Benford's law, and the last graph here are the 80,000 ledger balances for a large company that also conform very closely to Benford's law. Now for a little fraud data, a state of Arizona employee processed 23 checks for non-existent services performed by a fictitious vendor. The numbers that he invented had many more 7s, 8s, and 9s than would be expected under Benford's law, and for that matter, would be expected if the digits were equally likely. This graph shows the credits issued for kilowatt hours by an electric utility company. We investigated the spike at 99, and it turned out that several employees were fraudulently giving customers credits for numbers just below 1 million and just below 100,000 kilowatt hours. Those customers would in turn give the employees a nice present in exchange for the credit. To summarize, Benford's law works well to detect invented numbers when one person invents all the numbers, or lots of people each have some incentive to manipulate numbers in the same way, such as happens on income tax returns, Third point is that it is a useful start that gives us a better understanding of our data, and if we use it together with the other more focused drill-down tests to detect fraud, error, biases, and other anomalies, we should have a winning combination.